Hi, today I want to explain BERT1333 electrical circuit assignment topic transfer function. Now I want to introduce group members. First is Hanif bin Muhammad Zaki. Metric number is B122510176. Another one is 1 Muhammad Fidos bin 1 Zulkifli. Number metric is B122510188. Then Muhammad Ifan Daniel bin Rostin. Metric number is B122510149. Then my name is Chang Kok Wai. Metric number is B122510142. Introduction transfer function concept. A transfer function denoted as Hs is a mathematical model that describes the input-output relationship of a linear time invariant system. It is defined as the relation of the Laplace transform of the output to the Laplace transform of the input. Assume all initial conditions are zero. Ss is the Laplace transform of the input signal. Ys is the Laplace transform of the output signal. Then we can get the complex frequency variable.
Hi, good evening, everyone. Today I will explain how to rewrite a transfer function into the standard forms. From these forms is interested for identify the system gain, poles, and zeros. Okay, first step, which is we start with the given function. The equation was hash j omega equals to 5j omega plus 2 divide j omega bracket j omega plus 10. So our goal is transform each factor into the format a bracket 1 plus jw divide a. Okay, for the first step, the numerator, first let's look at the terms in the numerator, which is omega j omega plus 2. By factoring out of the constant 2, this become 2 bracket 1 plus jw divide 2. This given us a 0 at omega equal to 2. Okay, for the next step, the denominator, next we look at the terms which is j omega plus 10 in the denominator. Similarly, we factor out the constant 10 to get 10 bracket 1 plus j omega divide 10. This represents a pole at omega was 10. Before this, omega equal to 2. But this time, omega equal to 10. Okay, final simulation. Now we substitute this back into the original equations. So we put the equation to the first equation, which is h w h omega equal to 5jw plus 2 and j omega bracket jw j omega plus 10. So we put the new equation, which is 5 bracket 2 bracket 1 plus j omega divide 2 divide j omega that 1 plus j omega divide that. So when we multiply the constant in the numerators, 5 minus 2 equal to 10. So in the conclusion, after cancelling the constants, the final simplest standard form is, and you get the hence j omega 1 bracket 1 plus j omega divide 2 close the bracket divide j omega open the bracket 1 plus j omega divide 10 close the bracket. So that's a conclusion for transform the standard form to transfer the function into the standard form. So that's all for me. Thank you.
Okay, now I want to explain two magnitude plot. A magnitude plot displays the system gains h omega in a decibel dB against frequency omega on a logarithmic scale standard form. When the transfer function is rewritten into the standard form, 1 plus j omega over to omega c, too easily to identify corner frequency. Based on asymptotic smooth pole, each simple pulse, like the one at omega is 100. When cause the slope to decrease by 20 dB, is 0 omega 10 on the graph, cause the slope to increase by 20 dB when initial slope. When we see the graph, start with a downward slope of negative 20 dB. It indicates a pole at the origin. Then, when we can see the corner frequency, these are the points where the straight line approximately changes smooth corresponding to the value of pole and zeros in the transfer function. Okay, now I want to explain the fast boot block. The fast boot block illustrates the fast shift angles hj omega in degrees between the input and output signal. Fast calculation is the total fast is the sum of the angles of the zeros minus the sum of the angles of the poles. Fast shift. A zero constructs a total shift of plus 90 degree. The transition typically starts a descent before the corner frequency 0.1 omega and end a decade after 10 omega. A pole constructs a total shift of minus 90 degree. In the graph, we can see the fast dropping as it passing poles frequency. Poles as origin, this at a constant minus 90 degree starting fast, which match the initial fast.
So, from the graph, we can see this is a process of driving a transfer function from a back magnitude plot. So we can turn the graph into a mathematical equation. First step is how to find the gain k, which is we observe the graph start at the flat magnitude of 20 dB using the formula of 20 log 10 in 20 log 10k. We can get 20 log 10k equal to 20, so log 10k equal to 1, so k equal to 10. So we get the constant gain k is 10. So we can, step 2, we can identify the first corner frequency, which is we look at the graph where the graph change direction at omega equal to 10. So the slope change from flat 10 decibel going up to 20 decibel, meaning an output change indicate a simple zero in numerator. So the term standard is 1 plus j omega per omega naught since the corner is at 10. So 1 plus j omega per 10. And we can identify the second corner frequency, which is the pole. We can look at the next change, which is omega equal to 100. So the graph stop rising and it's become flat again. So the meaning, the slope was plus 20 decibel. To make it flat 0 decibel, we must add a negative 20 decibel slope. A downward influence indicate a simple pole in the numerator. Since the corner is 100, so 1 plus j omega per 100. And the step 4, we can identify the third corner frequency, which is we look at the final change point at omega equal to 1000. So the graph goes from 0 decibel to sloping down negative 20 decibel, which is this is another simple pole in denominator, since the corner is at 1000. So 1 plus j omega equal to 1 plus j omega per 1000. So the step 5, we assemble all the final function. We combine all the part using a standard transfer function structure, which is h omega equal to k multiplied by zeros per pole. So we find that h omega equal to 10 in bracket 1 plus j omega per 10 per in bracket 1 plus j omega per 100 multiplied by in bracket 1 plus j omega per 1000. So we can see the graph can be breaking down into individual component, constant gain causing the rise, and two pole causing the flattening and the fall. So for the discussion, we can analyze the behavior of the system based on our calculation. Regarding the system gain, the system exhibit a constant gain at a low frequency as we calculated. The initial magnitude of 20 decibel confirm a system gain of a k equal to 10. This means that at low frequency, the input signal is amplified by a factor of 10. Regarding the frequency response, the shape of plot is defined by three specific event. First, at 10 rads per second, the zero caused the gain to start increasing. At the 100 rads per second, the first pole counteracts that increase, causing the gain to level off at a peak of 40 decibel. Finally, at 1000 rads per second, the second pole caused the signal to attenuate or drop off for all the higher frequency. In summary, this plot characterizes a system that amplifies a signal significantly between 10 and 1000 rads per second.
Okay, my name is Muhammad Ipan Daniel Berosti and number metric is B122510149. And I will talk about effective transfer functions. So the 0 at the 10 radians and the pole at the 10 radians would theoretically cancel each other out, leaving a system effectively defined only by poles at the 100 radians and 1000 radians. In the phase transitions, the phase will start at the 0 degrees at the low frequencies. Each remaining poles at 100 radians and 1000 radians introduce a negative 19 degrees phase shift over a range of frequencies. The phase would drop 90 degrees around the 100 radians and another 90 degrees around 1000 radians. High frequency behavior at the very high frequencies, omega more higher than 1000 radians. The cumulative effect of the two net poles would cause the phase to stabilize at negative 118 degrees, not negative 90 degrees. For the conclusions, these conclusions effectively synthesize the frequencies characteristic of your system. Based on the transfer function, h omega equals to 10 multiplied with the 1 plus j omega per 10 divided by 1 plus j omega per 100 multiplied with the 1 plus j omega per 1000. You have accurately captured the system's dynamic behavior. For the key technical insights, zero pole synergy, the placement of the 0 at 10 radians counteracts the low frequency attenuations, while the dual poles create the necessary plateau on the band pass effect. This ensures the system effectively amplifies the desired range. Roll-off of stability. The analysis confirmed a control of beyond 1000 radians. Maintaining the phase response with the predictable limits is vital for preventing oscillators in active circuit implantations. So thank you very much, and this is the end of our discussions.